Hi everybody. So yesterday we went over a review of pH and what it means. Today I want to give you a quick lesson of some of the practicalities of pH, like what does pH mean to you in an agri-science and biotechnology course. And what I wanted to touch on here was acid rain. Now, acid rain forms when factories produce sulfates and nitrates. Usually that gets spewed kind of out of their smokestacks, and when it is up in the atmosphere, heat and light and all of these things can help to cause these sulfates and nitrates to combine with water vapor to form acid droplets. And that actually precipitates down to earth in several ways. The big way is acid rain. You can also get acid fog. You can also get acid smog. Now, we're not talking about a serious drop in pH, so if you step out in the rain, it's not going to melt your face off or anything like that. The problem is this acid falls to the ground, and it can end up either in the water, like this stream right here, as runoff, or it ends up in the soil. And the result is what you see in this picture down here. Up in the mountains, there's a terrible problem with acid rain because there's several things that acid rain can do. Number one, it can damage the leaves of trees. And the leaves, remember, are the sites of photosynthesis for the plant. So if the leaves are not functional, then the plant can't make its own food, and if the plant can't make its own food, it literally starves. Also, though, acid rain, when it leaches down into the soil, does two things. Number one, it can cause damage to the plant roots, but number two, it actually tends to dissolve nutrients in the soil that the plants actually need and leaches it down toward the bedrock in the soil and leaches it away from those plant roots, and so plants get malnourished as a result of acid rain. Now, all soils have what we call a buffering capacity. So buffering capacity is dependent upon what kind of soil you have. So farmers are pretty good usually about knowing what kind of soil they have. And around where we live, a lot of the soil has a lot of limestone in it, and limestone is important because it's made of calcium carbonate. Now, if you get a chance, look at the back of a bottle of Tums. That Tums is an antacid, right, which you take when you have too much stomach acid. If you look at the back of a bottle of Tums, it tells you that Tums is 100% calcium carbonate. It's actually basic. When you put calcium carbonate in water, it forms those little hydroxide ions, which means, remember yesterday you saw that neutralization reaction where if you put H plus OH minus, what you get is water. Okay, that's called the neutralization reaction. So you take these two kind of harmful ions, and when you put them together, you get something completely harmless. So soils that have a lot of calcium carbonate in them, in the form of limestone, are actually really, really good at buffering themselves, because when acid rain falls onto the soil, the calcium carbonate can actually go through a neutralization reaction with that acid and form water in the soil. Now, in order to deal with the effects of acid rain and problems associated with acid rain, farmers have a really easy method for dealing with that. Farmers use fertilizers, and fertilizers have a lot of nitrogen in them. And that nitrogen actually also buffers the soil itself. So because farmers are applying fertilizers to their crops, they actually don't end up having to deal with acid rain a whole lot. If you're talking about an organic farmer or someone like that, they're going to need to apply, or they're going to need to be testing their soil for soil pH, and just kind of watching their soil a little bit more carefully because they're applying less fertilizer. So that just gives you a quick impact of pH on agriculture and how soils kind of manage themselves.